Right, so we're going to be proving that 9 to the nth power minus 4 to the nth power is a multiple of 5 for all n in the natural numbers, so all the natural numbers. And we're going to be doing this by induction. So first, consider n equals 1. So this is our base case where we're going to show that this is true for one of the natural numbers, and it's kind of natural to start off with the first one, 1. So consider n equals 1, and then we have 9 to the first power minus 4 to the first power equals 5. So this is true for n equals 1, where 5 is a multiple of 5. So this equation works for the proposition that we have with 1. Now, next, consider some m in the natural numbers. So this is some arbitrary non-negative integer, natural number, and we have 9m minus 4m, and we assume that this is true, that our proposition is true for this. So we assume that this is indeed a multiple of 5. So what we've done is we've taken some random natural number and we're assuming that it is true. And based off this assumption, we can write the equality like this, where we have 9m minus 4m equals 5k, where k is natural number. So this is just representing what we've already written here, that this is true, where we get a multiple of 5. 5k will be a multiple of 5, where k is a natural number. So we now look at the next term. Which is n plus 1. And we get 9m plus 1 minus 4m plus 1. And we want to show that this is a multiple of 5. As if we can show that this is a multiple of 5, then we can show that the next term is a multiple of 5, and so on and so on and so on. So we're using induction to show that this is true for all the natural numbers. So, but we start off by considering the next term after assuming that the previous term is true. That satisfies our proposition. So now we've represented 9m plus 1 minus 4m plus 1, m plus 1 powered as this new expression. And it looks a little weird, but it's actually not anything different. We've just added in a 9 times 4m and then subtracted it, so we have this negative and then the positive 1. So these actually go to 0. And then we also have 4 times 4 to the nth power, and this is just 4m plus 1 expanded to 4 times 4m using exponent rules. So we have actually the same thing here, it just looks a little different, and it's going to help us show that this is going to be a multiple of 5. So then we go to pull out a 9 here, and we have 9 times 9m minus 4m, which if we go back over here, we pull out the 9, and then we're left with the 9m from 9m plus 1, and then we pull out the 9 here, and we're left with that 4m, so 9 minus 4 to the power. Additionally, we also have 5 times 4 to the nth power from this part of the expression, and we get this by factoring out the 4m first, and then we have 9 minus 4, and then we have 4m times 5, and that's what we have here. Now from earlier in the proof, we have assumed that this is true for m, where 9m minus 4m is a multiple of 5. So we can say that this 9 times 5k, or you could also write it as, Well, it doesn't really matter how you write it, but you know this is going to be a multiple of 5 because you're multiplying it by 5. And then also have that this is a multiple of 5. So to show that a little better, we can pull out the 5, and then we have now we have this all put together here. We have 5 times 9k minus 4m, where k and m are both integers. And we get this because we have that this equals some multiple of 5. And we had the 5 here. Then we pulled out the 5, and then we had 9k minus 4 to the nth power. So this is going to be some natural number. And 5 times any natural number is going to be a multiple of 5. So by induction, we've proved that 9n minus 4n is a multiple of 5 for every n in the natural numbers, for any natural number.